Oh, okay. I'll wait patiently. There we go. So yeah, cancel out the m's and v naught squared over 2g. Yep, it's super straightforward. So that one's not so bad. That one's relatively straightforward, not such a bad problem. And in fact, if I recall correctly, A did not really garner you too many points. But the next one's not so bad either. I'm kind of blocking the one that's going to be harder. So question B is the vertical component of the net force on the block. Is the vertical component of the net force on the block upward, downward, or zero? And I want you to justify your answer. The vertical component of the net force on the block, upward, downwards, or zero? You guys know that vertical is up and down, right? All right, that's probably enough time to think about that one. Now, they're not trying to trick you on this one. I'm interested in what this question is getting at. So let's see. Hannah, you've been selected as a participant on this one. Can you talk a little bit about what you think the answer should be? Hannah Bynum, please. And why would you think it's zero? In the participant column, how many of you agree with Hannah? All right, good job, everybody. So 27 of you think so. Of course, there are 30 of you, so that's a little rough. But yeah, net force will be zero in the vertical direction. Once it reaches the tabletop, and they are talking about passing point P, so we know it's on the tabletop at that point, so it's not accelerating up or down, so the net force in the vertical direction has to be zero. So here's where the problem begins to get interesting, and we might use our breakout groups a little bit for this. So this one I'm not sure you need your breakout group for. It says, on the figure below, draw an arrow starting on the block to indicate the direction of the horizontal component of the net force on the moving block when it's at that particular position. I want you to think about this one carefully, because this one could be confusing. So take a moment and draw a picture. You guys can't see it on your screen? So it's not updating. I understand what you're asking, but I have done that. It just hasn't updated your screen. So because I've been writing on the screen and everything, and I have a feeling you haven't seen any of that. So, can I see it better now? All right. So on the figure below, draw an arrow starting on the block and indicate the direction of the horizontal component of the net force acting on the moving block when it's at that position. So I'll take a minute and ask for this, normal force, the expression for the normal force. Net force has to equal MA. And only the part of the force that's causing it to travel in circular motion is the one that's is the normal force. So when we look at this, there are two components here acting on the system. And the one that matters for it going in a circle is the component that's in this direction, and that's the normal force. The other force doesn't cause circular motion, and because of that, I'm really only worried about this. So when I want to determine an expression for the magnitude of the normal force, in terms of V, then the only force acting to cause centripetal motion is that one. So this is all that you had to do for part C. Any question about that? Now D begins to get a little bit more complicated. It says derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained speed v. Now that's a little harder because the tangential acceleration is based on the tangential force, which is the frictional force. Is there no mu for part C? I don't believe mu is a part of it, no. Because all they're asking for is what the value of the normal force is. Now, on the other hand, I do believe we're going to use this normal force when it comes to friction here in a minute. So Jordan just asked a question. I'm trying to answer Jordan's question. So let's consider the next part of this. And I think we can do the derivation over here where my smiley face is. So bye-bye, smiley face. And let's consider that the tangential one is an unbalanced force in, the way I've drawn it here, the y direction. And that's going to be equal to ma, and I'll put a little t here to remind me that this is the tangential acceleration. This is the acceleration that is slowing the block down. Now, the force that causes this is friction. And the frictional force is mu times the normal force. And we know that the normal force is related to the velocity. So when I cancel out the m's here, I'll get that the tangential force is going to be equal to mu v squared over r. Any questions about this? Go ahead, Tyler. No, I think we probably need a negative sign here. I think it's a good idea that you bring this up. The frictional force is slowing the object down. It's acting, it's clearly acting in a negative direction, even based on my XYZ coordinate plane there. But yeah, I do think that we should have said that this is negative, which would make my acceleration here negative. You can always count on Tyler to keep us, set when it comes to dealing with positive and negative. Now, question E is the hard one, and one where we may or may not have enough time to finish it. But question E asks, derive an expression for the velocity as a function of time. And we have a differential equation here that we could use to figure out the velocity as a function of time. Now, I don't have room here to work on this part, so I'm going to put up a new screen. But I want to start this from knowing that the tangential acceleration equaled minus mu v squared over r. We want to determine an expression for the velocity. Now, I would expect that getting to this point wasn't terrible, but some of you probably hit some bumps on it. This next part, though, is procedural. It might seem like the hard part, but we have a differential here. We have acceleration. So this becomes less, I think, physics and more procedure. All I have to do now is do the derivative. Well, in this case, the integral. So I'm going to split my derivative. Now, I like to do this as a definite integral, but I know some of you from your calculus class are more interested in seeing this as a indefinite, but I'm still going to set my limits and just do it as a definite integral. This is not a particularly hard integral. There's nothing really fancy here. So we know that the initial velocity at time 0 is v naught. That's me setting my limits. And I'm going to be looking for v as a function of t in the future. Any question about what I've done to set the limits here? All right, we only have a moment to go before we're going to get kicked out. The left side is pretty straightforward. It's the right side that's going to take you a little more time. Now, nobody stopped me, but there's a mistake in all of this. I was hoping somebody would have stopped me before now. So the mistake is straightforward, and it's right here in the work. We can't separate the variables like this. In order to separate the variables, we need to get v on the same side as dv. So that's why this one's a little tough. So we need to back up to here. And make sure that when we look at this and separate out our variables, we bring 1 over v squared dv on the left and negative mu over r dt on the right. Just moving the v squared to the same side as my dv. Now I'm still going to have to do my integral. I'm still going to set the same limits. This is still going to be from 0 to t, while this is going to start at v naught and go to some v in the future. But now at least I've created the conditions where I can figure out what the function is, and I've got the v on the right side. So the left side, I need to find the function for this. This is just v to the negative 2 power. So I'm going to add 1 to it and have negative 1 over v evaluated from v naught to v. And the right side is just going to be mu r times t. Now, I still need to get the function together here. So here's where I have a ton of algebra. So putting in my limits, I'll have negative 1 over v minus negative 1 over v naught. And this has to equal negative mu r times t. We have to get v by itself. So this is the part that's a little tough. And the first thing I'm going to notice is that I can just multiply through by a positive there. That'll make it a little bit easier. And I'm going to move this term to the other side. So I'll have 1 over v equals 1 over v naught plus mu r times t. Now, this is not v as a function of t. You still need to get v inverted. So I want to invert both sides, which means raising both sides to the power of negative 1. The left side's pretty easy. It's just v. But the right side, that's kind of a mess. So one of the things we can do is get common denominators here and then do the inversion. That will make it a little bit nicer. So I'm going to have a common denominator of v naught times r. And on the left side, I'm going to get mu t. And on the right side, what am I doing, mu t? What am I thinking? That's not right. On the left side, I'm going to have r. On the right side, I'm going to have mu t v naught. So now I can actually invert. And I'll get v equals v naught r over r plus mu t v naught. And there we go. We have v as a function of t. And it's not a huge deal. It's not super surprising. We know t is in the denominator of a fraction, which is going to mean that it's going to get slower over time. Also, we need to make sure our units work out, and I'm just going to do this real quick. The top units are velocity, meters per second, times meters, but my answer needs to be a velocity. So the bottom better be a unit of meters, and it is, because r is in meters, and t times v naught is also in meters. So the meters will cancel out, leaving me something in terms of meters per second. This is not an exponential decay. This is just a standard decay, an inverse function. So the object, as it gets slower, it slows down even more because there's less pressure on it from the normal force. And as the normal force gets smaller, the acceleration gets smaller, which means the change in velocity gets less. So it slows down, and it slows down while it's slowing down. Well, there it is.